we need to get away from this idea in our head that electrons are fixed. Remember, electrons, they're whizzing around molecules. So, to explain resonance initially, we're going to look at our benzene. So, benzene explains this idea of resonance quite nicely. So, when we started off, we drew benzene like this, with my alternating single and double bonds.
Please don't tell us it's not like that.
No. Well, it's not. That's a Kepley structure. Would it have mattered if I'd drawn it like that?
Yeah.
Doesn't matter, does it? It's the same. These are resonance structures, and it shows because does benzene really look like that? If I had benzene in my hand and I could look at a molecule of benzene, would it look like that?
No.
No. It's just me as a chemist trying to represent it in a way that I, and perhaps you, can understand. Because I see that as a carbon, I can imagine the hydrogens coming off. But actually, if I was to look at benzene, it doesn't look. These are just representations of it. And these are alternate structures of what we can look like benzene. Neither of these exist. The reality is a mixture of the two. And to show that, I put a double-headed arrow like that to show that these are resonance structures of benzene. So neither of them actually exist in reality. They only differ in their placement of electrons. So resonance structures differ in their placement of electrons. Neither of them exist. And generally, the more resonance structure we can draw for a molecule, the more stable it is. Because it shows that I can spread my electrons out around my molecule. And that's why we draw benzene with a little circle in the middle, because that represents these two structures. So, how can I put curly arrows on to go from one structure to the other? Well, if I was to move that pair of electrons there, then that pair of electrons would go there, and then that pair of electrons would go there. And to go backwards, that pair of electrons could go there, that could go there, and that could go there. So we can use curly arrows in the same way that we've done with reaction mechanisms to show these different resonance structures. Yeah.
Do they always have to go clockwise?
No, you can do it whichever way you like.
So is it basically trying to, like the two structures show like benzene when it's still, like if you take a photo of it,
Yeah, that's
it's
right.
like it, and then
Yeah.
that's basically saying, well, this is like it not trying to show it in the video, but
Yeah.
still.
It is moving, yeah. In reality, neither of these exist. In reality, they're all whizzing around. But this is just me. It's like when I draw these molecules up, I draw them as static representations. In reality, those carbons are vibrating away, aren't they? And the hydrogens are all vibrating, the molecules moving around. But I just show this as a static picture. And this shows the movement of a pair of electrons in a covalent bond. So that's one way that we can do it. So this shows, if we just shows the movement. Shows the movement of pi bonds. The other resonance structures that we can draw involve lone pairs becoming double bonds and so on. So another example of resonance structure involves carbonyl groups, which again we've met before. So if I had propanone I could draw propanone like that. But I could also, if I wanted to go crazy, draw propanone like that. So how have I got from one to the other?
It's the plus on the
Plus is on the carbon. So how can I go so?
That bond is broken and gone to the carbon. So
That bond has gone from there
Yeah, because that's become negative.
to there. How can I go the other way? If that's my lone pair,
You go lone pair to the plus.
Plus.
the lone pair goes to the bond. So that just shows the movement of a lone pair to a pi bond. So there's the other example of resonance. So we can say, going that way, we have a pi bond to a lone pair. And going that way, we've got a lone pair becoming pi bond. Now don't get stressed about these. These are really useful, particularly as you're all going to go on to do a degree in chemistry. But they will help us when we come on to the next topic of phenol. And it also helps you just get an idea that these electrons are moving. How do we represent this? How have we represented this in the past, these two residue structures? What did we do when we drew? Not isolate. If I draw in that and I say, oh, the double bond, what would I put there? I'd put
Delta,
delta plus
positive, delta negative.
delta minus. Yeah, that's my average that we've shown as a representation. That's one extreme. That's the other extreme. In reality, neither actually exists. In reality, it's that.
In A2, you still have to use a delta plus.
Yeah. So when we do mechanisms, we'll go back to this. But this is just a useful, so you can kind of say, well, which one? It's not 50-50, it's more this one, with a ditchy bit of that one going on, you know? Because it's only a little delta plus and a little delta minus. But it helps us to show, and it just gets us used to showing how these electron pairs can move. And we've got to try and get away from this idea of this bond that is my molecule and the electrons don't move. The electrons are never bang in the middle and things like that. So it's just a useful thing to be able to do as we go on to resonance structures. Okay. So, useful stuff which we're going to now use when we go on to look at phenol, which is our next topic.